So finally we come to section 4.4, the fundamental theorem of calculus. That's a pretty impressive name. Let's recall what we've been talking about. So if we have a function, maybe it's the graph of the function's entirely above the x-axis, maybe it's not. And you have some x values, x equals a and x equals b. That gives us an interval between them. Then we've been talking about the concept of signed area. If the graph is entirely above the x-axis, we're talking about regular old area. But the definite integral from a to b of f of x dx is just the area enclosed between the curve and the x-axis. And we know that if part of the curve is below the x-axis, stuff below the x-axis counts as negative area. If it's all above the x-axis, it's just regular old area. But right now, we know the way we compute this requires a tremendous amount of work. We take this interval AB and break it up into little parts. We build rectangles. You get the area of each rectangle by taking the height of the rectangle, in other words, the height of the curve, and multiplying by the width of the rectangle. And then you add those all up, and then you let the number of rectangles go to infinity, and the widest rectangle get very narrow. That is a tremendous amount of work. You'll recall how much work that was when we did it just for y equals x squared, the parabola, between x equals 0 and x equals 1. It took us the whole blackboard. So, as you may have guessed from our earlier experience with derivatives, remember when we first started computing derivatives, you had to take the limit as h goes to 0 of f of x plus h minus f of x all over h, y2 minus y1 over x2 minus x1. So we saw the secant line getting closer and closer to the tangent line. And then eventually we learned rules for taking derivatives. Maybe there's a shortcut here. And there is, and that shortcut is called the fundamental theorem of calculus, which we often abbreviate as the FTC. There's really two parts of the fundamental theorem of calculus. We're going to talk about the first part today. So FTC part 1, or if I just refer to the FTC, the fundamental theorem of calculus, I'm almost certainly referring to the fundamental theorem of calculus part 1. So if the function f is continuous on the interval AB, and capital F is any antiderivative. Remember we talked about antiderivatives. Of lowercase f, then the definite integral between a and b of f of x dx is capital F of b minus capital F of a. Capital F of b minus capital F of a. Let's go back to that problem we worked so hard on. Find the area under y equals x squared between x equals 0 and x equals 1. So we have this parabola. We're going between x equals 0 and x equals 1, and we want the area under the curve between x equals 0 and x equals 1 of y equals x squared. And that's how we write it using definite integral notation. And again, the last time we were here, we worked incredibly hard on this, the last time we worked on this problem. We took this interval and cut it up into n parts. We computed the height of the rectangle. We did a right-hand sum. We computed the areas of all the rectangles by taking the height and multiplying by the width. We added those all up. We let n go to infinity. We had to use rules for summations. We worked really hard on this. Let's go ahead and see if we can use the fundamental theorem of calculus on this instead. So we're looking for an antiderivative. So in this case, my f of x is x squared. That's the function we want. We're looking for an antiderivative of x squared. Well, back in section 4.1, we got very good at doing antiderivatives of functions like this. We could just use the antiderivative power rule on it. So capital F of x equals 1/3, so 1 over 2 plus 1, x to the 2 plus 1. So 1/3 x cubed plus a constant. So the general antiderivative would be plus a constant. But this says any antiderivative. So I could put any constant I want after this, including 0. So when we're doing when we're doing definite integrals, you don't even have to put in the plus a constant. So according to the fundamental theorem of calculus, this is equal to, so let me just rewrite this problem down here, 0, 1, x squared dx. According to the problem, this is equal to f of 1, the right-hand endpoint, minus capital F of 0. Capital F of 1 minus capital F of 0. In other words, I'm just going to plug 1 in here and then subtract off what I get when I plug in 0. So 1/3 times 1 cubed minus 1/3 times 0 cubed. In other words, 1/3 minus 0, 1/3. We did this in 3 lines. Remember how much work we had on both sides of the board over here. The fundamental theorem of calculus is incredibly powerful. It deserves its moniker because it ties together basically what are 2 central processes in calculus. That of taking definite integrals, areas under curves, and that of taking derivatives. Let me just show you a notation for this. I'm just going to redo the problem we were just working on and indicate a notation for you. So we want the integral from 0 to 1 of x squared dx. Instead of writing all this business, you can just go ahead and write the antiderivative. So a perfectly nice antiderivative for x squared is 1/3 x cubed. You could use any other antiderivative you wanted. We're going to put it in square brackets, and then we're going to put these 2 numbers, the 0 here and the 1 up here. And what that means is plug this number into this and subtract off what you get when you plug this number into this. In other words, exactly the same computation we did over here. This is just a nice, neat way of writing it down. So 1/3 times 1 cubed minus 1/3 times 0 cubed. In other words, 1/3 minus 0, which is 1/3. So a nice, neat notation. So instead of going through all that trouble of breaking up your interval, building rectangles, computing the areas of all those rectangles, adding them all up, letting the number of rectangles go to infinity and the widest rectangles get narrow, we can just use the fundamental theorem of calculus. Assuming that we can take the antiderivative of whatever function we have inside. This function inside is called an integrand. So assuming we can find the antiderivative of our integrand, we're set.